Good evening, I'm Matt Windsor. This is the first time I've given one of these talks in this format, so bear with me and my hopefully at least tolerable microphone settings. This is going to be a talk about concurrency testing because that's what I've been doing for the past 2 years or so. But differently from the last time I talked about what I've been doing for the last 2 years or so, I'm going to be focusing on litmus tests, what they are, why we use them, why we might not want to use them, what we could do differently, and various things in that style. So without further ado, I'm going to go on to the next slide. Next slide, please. So generally, when we think about how our programs work, the first mental model you might have is something that might look a little like this. There's a processor, one processor, and there's a memory, one memory. And the programs that we write are going to read stuff from the memory, manipulate it, and write it back to the memory, possibly also using I/O and sound and vision and all of that stuff. But generally, we think of the processor in the singular and the memory as one thing that we need to deal with. Unless, of course, we've been reading Herb Sutter's The Free Lunch is Over, in which case we think more in these terms, where we don't have one processor, we have multiple cores, and all of these cores are all connected to the same memory, and therefore they're constantly in conflict with each other when it comes to reading and writing to that memory, for they share the memory, and therefore they can upset each other by writing to the same addresses at the same time and race with each other and do generally all the sorts of things you will probably have been told about in second year concurrency modules. Concurrency is hard, but wait, there's more. We have caches. What are caches? Well, they're little sort of like mini memories that sit between cores and the main memory, and the reason they exist is because memory is really slow and far away, and generally if you're working on the same bits of data quite a lot, you want them closer to the processor and more quickly accessed. So caches exist, and the cores have their own caches, and they satisfy reads from the caches, and writes propagate through the caches, sometimes right through, sometimes right back. I'm sure there are talks available that could give more details than I could possibly dream of, but for the purposes of what we're going to talk about in this talk, they're an absolute nightmare because things like this can happen where we have, say, one variable x, and the memory says that x equals 1. But the cache is all in different states that have different views on what the value of x actually is. One core has just written 2 to x, so it thinks that x is 2. One core had in its cache x equals 0, and it's just read that, and obviously neither of them are correct with regards to the memory, and they're all in their own separate worlds, and writes on one side won't propagate to reads on the other side for until there's some unspecific amount of time passed. And this is called weak memory, and the reason it's called weak memory is because the guarantees that we get about memory are not strong, they're weak. And it's an absolute nightmare because it's just very difficult to reason about. So caches are an issue with weak memory when they don't flush immediately into memory or propagate things from memory into the caches immediately. Views on variables can get stale and all over the place, and generally it makes things difficult. Writes don't become reads for an unspecific amount of time, and so on and so forth. But wait, there's more. reads and writes can be reordered. They can be reordered by the processor. They can also be reordered by the compiler. And all of these reorderings are done to try to make things faster, because we really want things to go a lot more fast. Gotta go fast and so on. But it also means that if you're not specifically saying what the orders between these things should be, you can end up in a world of hurt. And also, values can come out of thin air, in theory. In practice, this probably isn't going to happen, but in theoretical memory models, it can and will, and causes nightmares for theoreticians trying to reason about weak memory models. And wait, there's even more, because not all processors are as weak as other processors, and not all processors are as strong as your view on how this sort of memory coherence works. So most of us usually have this mental model in our minds of basically, if you've got a load of reads and writes on different threads, it should be possible to find a sequential interleaving of all of those reads and writes such that everything flattens out into a nice trace and everything is basically everything makes some degree of sense, and that's called sequential consistency. And in practice, it's almost never the case because of whole weak memory. x86 is slightly weaker than sequential consistency, but it's also well known as being a fairly strong memory model. If you're programming an x86, things probably won't go that wrong most of the time. But when you go into RISC machines like ARM, Power and RISC-V, then you're in trouble because they are weak memory models, and you're in a lot of trouble if you wrote your program, tested it on x86, then ported it to these ARM, Power and RISC-V systems, and suddenly you get weird concurrency behavior because the memory model is weak. So it's important to know what the behavior of your various bits of hardware is, and for that reason we have litmus tests. As the name suggests, litmus tests are designed to test little bits of weak memory behavior in a way that's fairly characteristic of the various bits of hardware, so you can distinguish various different memory models using a small amount of litmus tests. And they look like this. First, you have an initial state in terms of some sort of shared memory variables. Here, x and y are both 0. Then you have 2 threads of execution, or maybe more. And these are, in this case, x86 ones, where the first thread is writing 1 to y and reading x into a register. And the other thread is doing the mirror image. It's reading 1 into x and y into its register. And then you have some sort of post condition. In this case, it's saying that if we witness that these registers are both 0, then we're in a strange memory model indeed. Pardon me, in terms of the x86 expected behavior. And that's because we would expect in sequential consistency, and also as far as I know in x86, that either one of these threads will have written and successfully propagated 1 to one of these variables. And litmus tests are designed in such a way that they can be read by various pieces of software, so they get munged into a textual representation that looks kind of like what I showed you before, but is slightly more ASCII. So, once we have a litmus test, what do we do with it? Well, we have a choice. We either simulate it over a model of the particular hardware that we're interested in, and this can be done by tools such as Herd7 and more recently by RMEM. And this gives you a result in the form of every possible state that could be observed theoretically on a machine of that memory model, and also whether the post condition was satisfied or not. But we also have a different path. We can execute these litmus tests on real hardware. And that's interesting because you may want to know whether the hardware itself has any bugs or whether it's stronger than the theoretical memory model. And that goes through a tool like Litmus 7, and this is going to be the sort of thing that we're going to focus on for the rest of the talk, not the simulation, because that's a story for another talk. So, does C have litmus tests? Yes, it does. Why does C have litmus tests when it's supposed to be portable assembly that goes basically the same for every possible system? Or at least you'd hope it would. Well, in actual fact, C has a fairly nuanced idea of weak memory. It has what's called the C memory model with various what are called C memory orders. And this is a sliding scale of weakness versus strongness that the programmer can opt into depending on whether they want fast code or code that is strong. So we have sequential consistency at the very strong end of the memory order lattice. We then have relaxed at the other end. Relaxed, don't do it if you want to go to it. It's very similar to basically not having any guarantees at all about the memory model. There are a few things that are guaranteed, if I remember correctly. I couldn't possibly tell you what they were, but effectively all bets are off. And that's if you really don't mind it taking ages for your reads and writes to propagate. And then in the middle, we have release, acquire, and breaded eggs, acquire, release. And these are for constructing things like pairs of loads and stores, where you want a store to definitely turn up in the next load in that pair that happens in the future. You tag one as release and one as acquire, and it inserts just the right amount of fencing for that to work. So yes, C has litmus tests. You'd like them to look like this, with the initial state, 2 threads, and the post condition. In actual fact, they look slightly different, just to confuse everybody. They look like this. And you can see the same sort of thing is going on with the initial state and the post condition, but the threads are now things that look kind of like C functions, and they basically are C functions, but yeah. You'll notice that we have atomic underscore int, atomic underscore store, and atomic underscore load. And these are bits of the C11 atomic operations library. The idea is that you specifically tell C, right, I want these reads and writes and read, write, modify events to be atomic, and you can optionally pass in a memory model and you get a decent degree of control over things and quite a few guarantees as well. So that's what they are. Trying to do these things with non-atomic reads and writes is a world of pain. So how do we take these litmus tests and run them on hardware? Well, we wrap them up in what I call a Litmus Harness. And by wrap up, I mean literally transplant the source code from the inside of the litmus test and then add bits of auto-generated source that correspond to the other bits of the litmus test. And once we've got this Litmus Harness runs thousands of times. In fact, it will probably run about 1 million times, no exaggeration there. And this is because weak behaviours are very unlikely to turn up, and we want to cover as many bases as we can. We can't be exhaustive on real hardware, so we just run it lots and lots of times. It synchronises the threads after each sort of iteration of all the threads of the test, logging the results and resetting the initial variables so that we go around again. It also does a little bit of perturbance and general weird things to encourage weak behaviours in the memory model. And once we've got all of this lovely Litmus Harness, this fits into the testing approach as follows. We start off with the litmus test. We run it through the Litmus 7 tool. That produces this harness. We then compile it with a compiler of our choice, or optionally a compiler of Litmus's choice, which is invariably GCC. and we get a binary that we can then run, and it will do the various things of running this a million times, telling us which states we found, how many times we found them, and whether or not the post condition was satisfied. So that's cool and all well and good. So why am I interested in litmus tests? Well, it's because I've been working on a project called C4. It's short for C Compiler Concurrency Checker. And the idea here is we're using Litmus as part of a testing approach where we take expected behaviors in terms of violations of the C memory model. We use a existing tool called MemAI, which creates litmus tests that witness those strange behaviors. Those are small litmus tests like the ones we've seen, but we want to make the compiler's life a misery, so we use fuzzing to make the litmus test as big and as full of garbage as possible, and then we run it on Litmus and get a result. And this works fairly well, but there are a few issues when we come to use this Litmus tool and these Litmus tests. So one of the issues is that the Litmus format is fairly prescriptive. You have n threads, an initial state, and a final post condition, and nothing else. You have shared variables, but they're all scalars. It even has problems with, say, atomic booleans. So the Litmus format is quite restrictive when it comes to fuzzing. And we really want to be adding as much C weirdness as possible. It's hard to pass in languages that aren't C because Litmus expects C. You'd have to pass it a C litmus test that calls into an object file that is of a different language, and even then you run into ABI incompatibilities even between C atomics and C11 atomics, let alone things like Rust or Swift. And also, because we're transcluding this source of the litmus test directly into this harness and then compiling the whole thing, that bakes in this runtime and all the various command line arguments and different modes and everything that it supports. And so you end up with a lot of duplication when you're producing lots and lots of tests, lots of runtime copies. It's not very efficient, and if you change the runtime, it doesn't change the tests. So a bit like DLL hell, really. So in short, this is how Litmus and the Litmus test approach stack up. The harness language is C. It's fairly low-level C. It's quite difficult to read if you're not the people who wrote the program that generates it. The input languages are either C or assembly. It's very difficult to pass anything else in. The metadata comes directly from the Litmus test. It gets mangled into the C that goes into the harness. The method is source embedding. And it's good because it's production ready. It's had many years of research into how to tease out weak memory behaviours, and it takes litmus tests directly without any sort of pre-processing. But it's also limited to the subset of C that survives this embedding. Even things like trying to return from the internals of those threads starts getting difficult. And also the runtime is duplicated into each test, which kind of makes me twitch from a don't repeat yourself perspective. So, the question of the talk: can concurrency testing be liberated from the Litmus style? And here's what I've got so far. I've come up with two key ideas that have influenced where I think would be a nice area of effectively dissenting from Litmus tests and Litmus 7. So the first one is noticing that there are quite a few interfaces between the various bits of the Litmus test and the Litmus test harness that we could exploit to make things a bit more interchangeable. And one example is that only a small bit of this setup is actually specific to C11 atomics or C++11 atomics or the other bits that are sensitive ABI-wise. So things like the threads and parts of the shared state model are specific to the ABI, but things like, say, the post-condition checking and the top level harness, less so. There are also things that are specific to the test, but not necessarily specific to the ABI. And those could be separated out, and the whole thing could be separated from the bit that is literally the same for all tests. Also, the other key idea is that we could play to the differences in the use case that I'm using this for. So Litmus was originally designed very specifically for minimal test cases that explore interesting differences between bits of hardware in terms of weak memory behaviors. The compiler is so irrelevant that GCC is hard-coded into Litmus unless you specifically tell it to dump the intermediate C files. And also everything is sort of fire and forget. You can just run these tests and find out things about your hardware and jobs are good. And what we're doing is quite different. We're testing compilers mainly, and we're making lots of big test cases through fuzzing, and they want to be trying to exercise as much of the compiler as possible rather than the hardware. Though the hardware, of course, is still relevant. We want weak behaviors lining up with what the hardware is capable of. And also we assume that there's a lot of infrastructure outside this testing system that can do the heavy lifting for things like producing the right format of tests to pass into our tool. So given those two ideas, I've been working on a side project called, and I'm going to mispronounce this terribly, phenolphthalein. Probably easier to spell than it is to pronounce, weirdly. And the idea of this is, it's Litmus but different. It's colourless and pink instead of whichever colour Litmus goes. I've drawn an absolute mental block for that. But the main idea of phenolphthalein is that we have a distinction between the compile side bit of test preparation and the runtime. And as you can see in this little diagram, we're actually going to be running a dynamic library that contains the test. And this is very different from the source inclusion that we had previously. And we create that dynamic library, for instance, not necessarily, but for instance, from taking a Litmus test and extracting out the thread bodies and extracting out the metadata, transforming that somehow into some C that we can then compile against the ABI or the API exposed by phenolphthalein, and also the test, and then we produce a dynamic library. And as long as that dynamic library exposes the right symbols, we don't actually care how that comes out, how this test was put together. So we already know that this is going to be quite different. So phenolphthalein is written mostly in Rust. It's really scary Rust. A lot of it is things that are unsafe, but I've put them into the safe Rust language because I'm terrible that way. Anybody who's really good at low-level Rust atomics, ping me afterwards. And it can take anything at the moment that links against the CABI. Ideally, we'd abstract that even further and have different ABIs. That's something that's on the cards for later. The metadata comes in through some C boilerplate, which I'll be showing you in a few slides' time. The method is dynamic rather than source embedding at compile time. And there are different pros and cons. Pardon me. The pro is that the input can be anything, as long as it exposes the right symbols of the right ABI. There's a possible extension to other ABIs, which I'll show a bit of later. And there's only one copy of the runtime because the runtime dynamically links against the actual tests. And everything that's in that runtime is generic across tests. So there are a few disadvantages of this approach, one of which is that it's currently very unstable and very beta. I'm still exploring this. It's not easily deployable because the runtime is a big wad of Rust with loads of dependencies, whereas Litmus 7 is very specifically designed so that you can cross-compile and copy zips over to embedded systems and so on and so forth. And there's currently a lot of boilerplate that needs to be created, and massaging Litmus tests into that boilerplate is something we can automate, but it's still a little clutch. So here comes the deep dive. You're very welcome to micro sleep through these next slides if it doesn't interest you. Hopefully it will interest some of you, but here goes. This is what a test looks like in phenolphthalein. And you'll notice that we have the thread bodies again, but everything else is different. So here we have the test function, and that serves as the single reliably ABI compatible entry point that phenolphthalein has to the test. It takes an environment structure. It also takes a thread ID, and it delegates to the right thread with the right bits of the environment, i.e. the shared state that the particular thread body is going to be reading to and writing from, and also the local state, because we want to be able to read the local state afterwards. So we actually sort of hoist local state to global state. And then you'll notice the post condition has become a C Boolean function, and that means that theoretically we could do anything as a post condition, though generally we'll be doing the same thing that we would in the litmus test, just directly over this environment. And what phenolphthalein will do is every time it comes up with a new state it hasn't seen before, it will call into this check and behave according to whether this returns true or false. So in phenolphthalein, every bit of this is abstracted to some degree at some point. So the test function ends up becoming something in Rust that looks like this, and the check function becomes this. And you'll see that they're very similar, but there is a little bit of abstraction over exactly what the environment looks like and exactly what the outcome is, and so on and so forth. So the environment itself is fairly high level in terms of what phenolphthalein sees. What the test sees is the actual representation that it can point arithmetic into, and so on and so forth. But here we have getters and setters that do not leak the atomic ABI, and that's important because of the differences between various languages that would normally be foreign function interfaceable into C. They all have different ABIs for atomics, so we erase that at the phenolphthalein level. All of this fairly lowish level C gets hoisted out into a nice trait where things are just clonable. You can clone handles to an environment. It makes borrow check aficionado scream because we're passing around mutable shared state, but that's the point of the test. We also then have the manifest, which covers all the various bits of the litmus test that would usually be metadata that would be extracted into C by Litmus 7. Here you'll see we've got a number of threads. That's implicit in Litmus. You just count the number of thread bodies. We then have, for each type of variable, and we currently only do integers, the number of those integers, their initial values and their names. And eventually this gets hoisted into a fairly pleasant API where you just have maps from strings to variable records, and it's all hunky-dory. And I would here give a demonstration of phenolphthalein, but I'm not entirely sure how to interface that with Keynote's voice recording feature. So instead you shall just have to git clone phenolphthalein and play with it yourselves, which I'm sure at least 0.01 of you will do. Anywho, thank you very much for bearing with my incredibly dry throat over the course of this single take, and also the ASMR-esque background noises that my incredibly sensitive microphone has been picking up in the duration of this half an hour. If you have any questions, do not hesitate to go over to the Discord Q&A, where I will be fielding those answers to your questions and generally hanging out. Thank you very much. I've been Matt Windsor. This has been a talk about phenolphthalein, which may be the future of compiler testing and litmus testing and other kinds of testing. I have no idea. It's a side project, so probably not. But hey, at least it's interesting, and it's a really good excuse to learn some Rust. Thank you kindly. End of slide.